Okay, so yesterday we discussed about this sequence item and what are the things we need to write in our sequence item. Okay, so then next sequence. Okay, in the sequence, write sequence and read sequence, how the handshaking is happening in our task body method. Okay, so all are implemented, right? So this is the read sequence with some virtual task like tickqvm do. Okay, so tickqvm rand send, all these things we have implemented. Sequencer. Okay, sequencer is written or extended by UVM sequencer. Okay, sequencer, what is the purpose of sequencer? It is a bridge in between the sequence and driver. Okay, so there is no extra logic we are added in the sequence, just we need to represent the class. Okay, your class name extends from the base class and parameterized class. Okay, so that means sequence items, it is carrying. Okay, it is transporting the sequence item to driver. Okay, so because it is a bridge in between the sequence and the driver. Okay, so then the custom constructor, that's it. Okay, most of the things, class registration, that means factory registration, equivalent component details, and then memory sequencer. After that, what is the things? uh, Constructor. Okay, custom constructor. Okay, so this is what basic sequencer. Okay, so anything else here? Just class representation, and then it is extending from the parent class, that is a UVM sequencer, and my class name is memory sequencer. In that, after that class representation, we are registering the class, that is factory registration. By using UVM macros, we are registering the class, take UVM component details, and then memory sequencer. After that, constructor, custom constructor. That's it, nothing else. Okay, sometimes we can also represent different uh, uh, custom constructors. Okay, so different custom constructors, how we are representing. So this is the basic thing actually we are representing. Okay, okay, I told you sequencer act as an arbiter. Okay, or mediator between sequence and driver. Okay, so that is the arbiter or mediator in between the sequence and driver. See, it manages the flow of sequence items from sequence to driver. Okay, it will manage that. Okay, how it manage that? So it think of mailbox or traffic controller from the for the transactions. How the mailbox is carrying the transactions, right? Same way, the sequence item is also carrying the transactions. Okay, so sequence items, nothing but stimulus. Okay, so that means it is controlling the traffic. Okay, so whatever the driver is having, it will control that traffic. Okay, so that means whatever the sequence items generated by the sequence, it will carry that and passing to driver. Okay, so next, then what is a UVM sequencer? See, UVM sequencer is a component. Okay, so it receives sequence items from the sequences and arbitrates between multiple sequences. See, not only single sequence, it is running on parallel, it will control that multiple sequences. Okay, and then forward sequences items to driver. Okay, whatever the sequence items we are generated by the sequence, and then it will forward to driver. Okay, and manages handshake protocol. Okay, handshake protocol between sequence and driver. Okay, you know that protocol handshake. What is the handshake mechanism? create the item, and then this start item, after that randomize, finish item, and then in driver side get next item and item done. Okay, so these handshaking is controlled by sequencer. Okay, so the key concepts here, so it is extending from, so extends from sequencer, right? Sequencer is my parent class. Okay, so then whatever my sequencer or memory sequencer, whatever sequencer user defined names, you can extend from sequencer. Okay, so it is a parameterized with sequence item type. Okay, I told you, so class my memory sequencer extends sequencer hash sequence item. Okay, so that is the parameterized class. Okay, whatever the sequence item is we are having, so that will be parameterized. Okay, so usually minimal code is required, no customizations. Okay, simply class registration, after that constructor, that's it. Okay, most of the things we are having same things. Okay, same. So it sides between the sequence and that means sequences. Okay, that means stimulus generators and driver, that means DUT interface. Okay, so driver is the DUT interface, sequence is driving the stimulus, so generating the stimulus, and then it is passing through driver. Okay, sequencer is the carrier. Okay, so it will carry that start items and finish item of the protocols. Okay, handshake mechanism it will carry. So whatever the, where we are starting the sequence item, where we are finishing the sequence items. Okay, it will carry that say handles. Okay, so handle is nothing but request or something transaction we are representing, right? So that is the handle. See, this is the UVM architecture. Okay, so how we are flowing that? First, we need to create the test. Okay, after that, the sequence will generate the sequence items. Okay, sequencer will carrying the sequence item, and then it is passing to driver. Then driver is transferring the sequence item to DUT. Okay, so this is the basic transaction. Okay, so how it is flowing that? First, you have to create the test. In that test, you need to start your sequence. Okay, so they will ask you where you are starting the sequence. In test, I'm creating the test. In test, I'm starting my sequence. Okay, start the sequence on the sequencer. Okay, so after that, sequence calls that start item. Okay, through handle, that is the transaction, and sequencer grant the access. That is the right sequence will generate the sequence will request the sequencer. Is there any sequence items are required? Okay, driver will send the request. Then sequencer will grant the request. Okay, so then this is the sequencer grant the request. After that, sequence randomize the transactions. Okay, it will randomize the transactions. Then what it happens, sequence calls the finish item. Okay, then sequence will send the sequence item to driver. Okay, send to driver. This is the handshake mechanism we are seeing, right? Okay, and then driver gets the transactions via sequence item code dot get next item. That is the driver handshake mechanism. Okay, sequence item code dot get next item. After that, driver drives the transactions on DUT interface. Okay, so if you take virtual interface or normal interface. Okay, so virtual interface is the interface between the DUT and driver. Okay, so through virtual interface it is driving the sequence items. Then driver calls the sequence item code dot item done. Okay, once you done the items, okay, it will call, the driver will call that item done. Then sequence will stop the sending of sequence items. Okay, so then sequencer notifies that sequence that transaction is complete. This is the handshake mechanism in between the sequence, sequencer, and driver. Okay, see, this is the basic sequencer. Most of the common we are using type def. Okay, simple type def we are using. See, uh, for most use cases, you only need to type def of sequencer. Okay, that is user defined sequencer. Okay, so then this provides all standard sequencer functionalities. Okay, So whatever sequencer you are taking, all standard functionality it will take that. Okay. See, this is the type def UVM sequencer, and then so what is the parameterized class we have taken? So that is the example transaction and then example sequencer. Okay, this is way in this way we are using type def sequencer. Okay, from this we are extending the classes. Okay, so then most of the test benches, that means 90% of test benches we are using type def sequencer. Okay, so then so type def will create the sequencer. Okay, so that accepts the example transactions. Okay, that means sequence items it is accepting. Example transaction is the your class name. Okay, in that class what we are taking, sequence items. Okay, that is the parameterized class. And then provide standards arbitration. Arbitration means communication, okay, or mediator. Okay, like a default it is like a FIFO. Okay, FIFO it will store the some transactions, right? Same way sequencer also will carry the transactions. Okay, so handles sequence to driver handshaking. Okay, sequence to driver handshaking is also handled by sequencer only. Okay, that is already we have seen, and supports all standard UVM sequences because sequencer is a controller. Okay, traffic controller. So that means it is a some manager type. Okay, so it will control that all the uh, whatever lower engineers are there, so manager will control that. Same way sequencer also it will control that transactions. Okay, see, this is the custom sequencer and advanced with additional features. Okay, how we are creating that? See, custom create a custom sequencer when you need. Okay, so whenever you need a class you can create the custom sequencer class. Memory sequencer extends UVM sequencer. In that way we need to create the class. Okay, and then additional configuration parameters also we need to add. After that, debugging or monitoring capabilities we are having. Then communication with the test bench component. Okay, so sequencer will communicate the test bench components. Okay, see, this is the class. Okay, example custom sequencer. Okay, you are designing a class. Okay, you are creating a class. Where you are creating from? Parent class. My parent class is UVM sequencer. Okay, how we are parameterized? Star hash example transaction. Example transaction is my transaction class. From the sequence items, we are extending the class that is the example transactions. Okay. So previously we are using right a sequence item. Okay. In that sequence item, we are the class name is example transaction. That is the parameterized class. Okay. So this is the registration. Register with UVM factory. How we are registering? Tick UVM component details. Okay. So example custom sequencer. That is my class name. Okay. Then some configuration parameters I am mentioning, right? So what are the configuration parameters I am using? How many transactions are pending? Okay, is int max pending transaction, that means 16 I am taking because in the number of transactions the range I am taking 4 to 16 in the sequence item. Same way I am considering that maximum pending transactions are 16. Okay, and then bit enable transaction is equals to 1. That means we are enabling the transactions, right? Same way, so how many bytes are enabled? Byte enable we are taking which byte having my valid data and which byte I'm having invalid data. So every time byte enable bit, one bit should be high because it is a 4-bit byte enable we are taking. So every time at least one byte should be enabled. Okay, that means one byte having a valid data. Okay, so then statistics counters, that means how many transactions are completed and then how many read are happening, how many writes are happening. Okay, it will count that. Okay, in this way I have implemented some custom constructor configurations. After that, some custom constructors. See, analysis ports for broadcasting, right? So that means it allows the components to observe the transactions. Okay, how the sequence item is giving the transactions, it will observe that. Okay, sequence items will transfer to driver through sequencer, and driver is passing the sequence item to DUT, then monitor will observe that. Okay, so monitor will observe that. So then I'm using UVM analysis ports. See, UVM analysis ports, example transactions, item collected ports. So this is the analysis ports we are implementing monitor, right? Okay, in the monitor side, I'm observing the number of transactions, how many transactions are done, how many are not done. It will observe that. Okay, so that's why we are implementing the analysis ports. After that, custom constructor. See, the custom constructor, what is the name? Function new, string name. So example custom constructor, and UVM component parent, that is null. So default it will take null. Okay, and then super dot new name comma parent. That means, so whatever the parent components are there, it will fetch that. Okay, and then see, we are creating the memory for this item collected port in the custom constructor. Item collected port equal to new of item collected port comma this. Okay, in this way we are creating the object. Okay, or memory. In the build phase, what we are creating, in the build phase, we are getting the configuration DB. Okay, so whatever the config DB we are setting in the top, okay, we are getting in the build phase. See, virtual function void build phase, UVM phase. Okay, so then super dot build phase. Okay, this is the basic syntax of build phase. After that, we need to get the components. Okay, config via config db. Okay, so then, so get configuration from the UVM config database if it is available. Okay, if it is available, I'm getting the configuration. How I am getting the configuration? If not UVM config db integer, type is integer. Okay, and then scope resolution get this means for this component, and then empty space for it is applicable to global. Okay, and then what is your instant string field name? Max pending transactions. Okay, I'm getting the how many transactions are pending. Okay, then the max pending transactions I want to show the I'm getting from the config table. If it is happening, I'm not getting any error. If it is not happening means, see, get type name, that is the type name we are using. See here, type name I'm using, right? So then building custom sequencer, this is my description. Okay, so and then UVM verbosity level, UVM high. Okay, so same type, that means get type name, I'm getting the name, whatever the parent component I'm having, that name I'm getting that. Okay, so same way, so $s formatter, it is converting some normal integer to string format. Okay, so then we are representing the transactions, how many transactions are pending, that means the maximum transactions I'm getting here. Okay, so this print, it will show that how many transactions are pending, and then UVM medium is the verbosity level. Okay, so see, I'm getting the enable transaction log also, because we are configuring, right? So maximum transactions and then enable transactions, then I'm getting the configurations. Okay, so some configurations we are writing, that's why in build phase we are writing the configurations. Okay, so maximum transactions pending as well as enable log. Okay, enable transaction log, that is I'm writing. Okay, clear? Same way, I'm ending the build phase. After that, monitor transaction flow. We are observing that. How the monitor transaction flow we are getting. See, virtual task run phase, UVM phase. So example transaction is my class. Okay. So handle I'm using for that, because I'm getting the sequence item in monitor through handle of this sequence item class. Okay. That is the example transaction. Okay, so then forever begin, so forever begin, then this is a non-add transaction. Okay, so that means forever begin, it is begin the transactions, how many transactions it is doing that. Okay, it will end that. Okay, you can use this additional monitoring or logging purpose. Okay, so while you are observing number of transactions, you need to see the number of transaction is happening or not. Okay, so then typically note this advanced usage is not needed. Okay, so this advanced usage, actually sequencer we are writing class registration and then constructor. This is the advanced sequencer we are using. Okay, custom constructors and configurations, all these things we are implementing. Okay, after that most of the sequencer just handles the built-in transaction, built-in TLM communication between the sequence and driver. Okay, so most of the sequencer only doing the same operation. Okay, in the advanced only we are using this type of sequencer. Okay, after that, custom log. What is the custom log we are using? So custom method, what is the log transaction statistics? What are the transactions it is doing? So we are uh, checking that number of transactions are pending, how many are pending, by using enable transaction log. Okay, enable transaction log begin and then transaction count is incremental. Okay, so what is the handle of your transaction class? Txn. Okay, if you are doing read operation is read, then read count will be incrementing. If it is not doing, then I am doing the write operation. Transaction dot is write operation we are doing, then write count will be incrementing. Then I am checking that how many transactions are completed, and then so transaction type name and then address. Okay, while doing read operation we are getting the address. Okay, while doing write operation we need to get the transactions. Okay, so in the monitor side, we are implementing this analysis ports, item collected port dot. So or sometimes we are using analysis ports dot write method we are implementing. This write method we are calling on scoreboard. Okay. See, printing the statistics, how we are enabling the transactions, what type of transactions are done, and then how many are pending, is that enabling transaction or not. So all these statistics we are printing here. Virtual function void report phase, UVM phase, super dot report phase. Okay, in the report phase we are printing the transactions. Okay, see, UVM info, get type name. So by name only we are getting that. Okay, and then $s format F sequences statistics, total transactions, percentage 0D, and how many read transactions are done, how many write transactions are done. It will show that. Okay, total transaction that will printed on the transaction count, and read transactions that will be noted from read count, and write transactions it will be printed on write count, and then verbosity level is UVM low. Okay, this is the custom method to print the statistics. Okay. After that, again check sequencer if the sequencer is in busy condition or idle condition. Okay. We need to write some construction like function bit is busy. Okay. Is busy means it is doing some other operations. Okay. So return m sequence m request FIFO dot used is greater than 0. That means, so if it is busy means it will print this value. Okay, it will return this value. Function will return one value, right? So then we are writing some return value. Okay, so how many transactions are stored? Okay, so check any sequences are running or any transactions are pending, or if you are synchronizing with some complex transactions or not, it will check that. Okay, after that, get transaction pending count. How many transactions I am having pending? Okay, then I need to get that. Function int get pending count. Same way in the FIFO, how many used, then how many are not used, we will get the pending count. Then get the pending count, it's ending, and then my class is also ending. Okay, so this is advanced sequencer. Okay, so actually sequencer is carrying the transactions only. For that class registration, and then custom constructor, that's it. If you want to go for some advanced, some configurations we need to call, and also for that we need to design some custom constructor, and read count is happening or write count is happening or not. For that we are writing some functions. Okay, clear? Just give me a minute. Same way, virtual sequencer. Okay, so we are taking the support from virtual sequence support. Okay, sequencer with virtual sequencer support. Okay, so I told you right. So we are using some two handles like M sequencer and P sequencer. Okay, see, when you coordinate with multiple subsequencers. Okay, so why we go for virtual sequencer means, or virtual sequence means, so we go for multiple sequences, so subsequences we have, so then we go for virtual sequencer. Okay, see, if when you need to coordinate multiple subsequences in complex test bench, whatever the complex test bench we are taking, at that time you need to create a virtual sequencer. Okay, that refers the sequencer. Okay, so that refers the other sequences. Virtual sequencer is the manager. Okay, it will control the traffic on the driver interface. Okay, see, class example virtual sequencer. Okay, extends from sequencer. Okay, so that is my class, and then registration with some parameterized class. Okay, so no parameterized for virtual sequencer. Okay, previously we are using parameterization. So for virtual sequencer we are not using any parameterized class because it is not physically appear. Okay, so that's why we are not using any parameters. And then registration class take component utils example virtual sequencer. Okay, so then uh, this is the reference subsequences. Okay, references to subsequences. How we are referring the subsequences here? See, virtual sequencer doesn't generate transactions itself, right? So virtual sequencer doesn't generate any transactions, right? So just it holds the reference to actual sequencer. Whatever the actual sequencer we have, that it the virtual sequencer will holds that. Okay, using for holding purpose only. Okay, so for that I'm using some example sequencer. So memory sequencer. Okay. So that is for memory sequencer interface. Okay. And also how many sequencer it is generated, I am controlling that. Control sequencer also taking for control interface sequencer. Okay. So if you are operating multiple sequencers, we go for memory sequencer and control sequencer through virtual sequencer. Okay, so this is the custom constructed function new. So what is your class name? Example virtual sequencer component parent equal to null. Okay, super dot new name comma parent. After that we are creating the memory for that. Okay, by using get type name we are calling that. Okay, so get type name super virtual function void build phase phase super dot build phase. Okay, so in that we are calling by get type name. By name only we are calling that because we have mentioned some virtual sequencer. In that some handles we have mentioned memory controller, and then so memory sequencer and controller sequencer. Okay, so by name only we are calling. This is the basic example virtual sequencer. Okay, so now I am creating some examples, creating and using basic sequencer in agent. Okay, see, virtual sequencer is a manager. Okay, it will not hire any other people, agent only hiring, right? So that's why virtual sequencer does not generate any sequences. Okay, sequence items or transactions. Okay, agent only it is doing that because in that only we are having some sequence. Okay, so in that we have sequencer also. Okay, so this virtual sequencer will hold that actual sequencer. Okay, see, class example agent class example agent extends from agent. Okay, so this is my class representation. After that, sequencer instance. What is the sequencer instance? Example sequencer. Okay, and also driver instance. In the agent we are writing, right? UVM agent I am creating that. Okay, in agent what we are having? Sequencer, driver, monitor. Okay, all the handles we are representing here. Okay, so then function void build phase, super dot build phase, UVM phase. Okay, sorry, super dot build phase. In that we are creating the memory for that. Sequencer equal to example sequencer type id create sequencer comma this. Okay, after creation of sequencer handle, driver handle also we are creating. Driver equal to example driver type id create driver comma this, and then end function. So in build phase we are creating the object. Okay, after that connect phase we are connecting, right? So function void connect phase, UM phase, super dot connect phase. Okay. So how we are connecting? Driver instance dot sequence item port dot connect sequencer instance dot sequence item export. Okay. So this is the agent, basic agent we are creating. So just I am creating and using basic sequencer in agent. Okay. So that is the basic agent we have created. Okay, then starting a sequence on sequencer from test. Okay, so whatever the sequence you have created, that you need to start the sequence. Okay, in test we are starting the sequence. See, class example test extends from UVM test. In test I am creating the handle for environment because in the inside the test environment is there, right? Okay, and then task run phase, UM phase. Okay, simple random sequence. So that is the handle is sequence. Okay, simple random sequence is the class name. From that I am creating the handle is sequence. Then phase dot rise objection. So sequence equal to simple random sequence type id create sequence. Okay, so creating the memory. In the phase rise objection we are starting the sequence, right? So start sequence on the sequencer. That's for that sequence dot start, where we are starting the sequence. Okay, so environment dot agent dot sequencer. Okay, so in that way we are starting the sequence. Okay, after that phase dot rise up drop objection and task end class. So we have started the sequence in test. After that driver is getting the sequencer. So for that I am creating the driver class. Okay, so sequencer, how? First we have created the sequence. After that in start we are starting the sequence in our test. For that we have created the test, and then we are driving the sequence item. Okay, for that we have driving the we are creating the driver class also. Okay, class example driver extends from UVM driver. Okay, so before that you need to represent all the class registration, custom constructor and build phase, config db we are representing. After that task run phase we are writing. Okay, task run phase, UVM phase. What is your example class? Okay, example transaction handle is transaction. Okay, so then forever begin, my handshake mechanism is happening here. Sequence item code dot get next item of transactions. Okay, my transactions I'm getting here, and then here driver transactions. So driver transactions for DUT interface. And then so this is, if you are writing all the inputs or stimulus, here only you can write, or in between the driver sequence driver handshake mechanism you can write some driver transaction. For that you can write another task. In that way also we can write. Okay, and then sequence item code dot item done. Okay, so I'm completing my handshake mechanism between the sequencer and driver. Okay, then end task end class. Okay, same using custom constructor with statistics. Okay, so custom sequencer, how we are sequencing? See, the sequencer is transferring the sequence items, right? So example class test extends from UVM test and then environment test, task run phase. So we are having some sequence handling. After that example sequencer we are having custom sequencer is the handle. Okay, and then phase dot rise objection drop objections we are doing that. Then we are driving the sequencer, custom sequencer. Okay. So then, what is the things we need to write here? Cache to custom sequencer to access additional features. If you want to write additional features, configurations, all these things we need to write. Okay. See, cached custom constructor and sequencer environment dot agent dot sequencer begin, and then UVM some fatal we are writing. Okay. So in that fatal some fields are not customized, and then all these things we need to write. If you are not go for some advanced, then we can leave it. Okay. Then virtual sequence, using virtual sequencer. Okay. So UVM sequence is my class, and then example virtual sequence I am creating here. Okay. After that, tick UVM object details example virtual sequence class registration it is happening. Okay. For that UVM declared P sequencer. See, so UVM declared some P sequencer, that is for example virtual sequencer handle. Okay. So then task body method simple random sequence memory sequence item, then control sequence is the handle for that. Okay. So then memory sequence, and then we are creating the simple random sequence. Okay. Then memory sequence is the another handle for the memory sequencer, and control sequencer is the another handle for control sequencer. Okay. M sequencer is the M sequence is the memory sequencer handle. We are creating that. Then I'm starting that memory sequence dot start P sequencer dot memory sequencer. Don't use M sequencer here. Okay, M sequencer is the handle of sequencer, so that is the base sequencer handle. So don't use here. There is no authority to write. So to create to control the traffic here. Okay, P sequencer was the only manager to control the traffic. Okay, so because virtual sequencer is the controller. Okay, it will control the sequence items. So then run the sequence. See, control sequence same way. Run sequence on control interface for parallel or serial. Okay. So again we are creating the memory control sequence simple random sequence type ID create control sequence. Okay. Again I am starting the control sequence. Control sequence dot start P sequence dot control sequencer. This is where we are creating the virtual sequence. Okay. So this is the key takeaways. Basic sequencer. Usually we are using type def, user defined, and simple standard functionality. No need for custom class. Okay. So simple custom sequencer. Okay. And then custom sequencer. How we are writing transaction statistics, custom arbitration, additional debugs, and communication to the other components. That is the another sequencer we are considering. So advanced level. Virtual sequencer. So what is the purpose of your using virtual sequencer? Multi-interface design and coordinating multiple sub-sequencers. Okay. So that for that purpose we are using virtual sequencer, and we can also build complex test scenarios. Okay. What is the sequencer role? Mediator between the sequence and driver, handles TLM communication, manages transaction flow, provides arbitration. Understood? Okay, this is all about sequencer and virtual. Next, driver. How driver will driving the sequence items. Okay, see, driver is converts transactions from the sequencer into pin level signals. Okay, so here sequence items are in packet level, then it will convert pin level. That drives the DUT interface. Okay, it implements timing and protocol. Driver will implement as well as timing, and then protocol also it will implement. So this is the driver class example driver extends from UVM driver. Okay, so that is the example class. Okay, so we are considering, and then class registration with UVM factory. Okay, tick UVM component details, example driver. Then virtual interface to DUT, because in real test bench what we need to do, so virtual example interface VAF. This is the virtual VAF is the virtual interface handle. Okay, so this is the real test bench, real test case scenarios we are using virtual interface, because your test bench is in dynamic nature and DUT is in static in nature. For that, no nature is does not changing. We are using virtual interface. Okay. After that, custom constructed function new string name, uh, your class name, example driver, and UVM component parent equal to null. After the super.new, we are extending, we are getting the parent class properties, and then ending function. In build phase, we are creating the virtual interface, right? So, and then in the top, we are setting the config db. In the build phase, we are getting that config db virtual function void build phase, event phase, super dot build phase, and then by name we are getting the information. Okay, so tick info get type name, by name only we are calling that. Okay, see, get virtual interface from the config db configuration database we are using. So if not using config db virtual example interface, okay, virtual example interface, that is your handle, okay, virtual example interface. For that handle we are using VAF, okay, and then scope resolution get. This is used for current component, and then empty space for global, and your interface name is instance name is VAF, and from VAF we are getting the data. If it is not getting, then you will get some fatal error. Okay, so if you are failed to get the virtual interface, then it is getting some fatal error. Okay, then end build phase. In run phase, what we are doing, we are initializing the signals. That means we are following some protocol, right? And also UVM driver will implement it. Okay, in run phase, main driver phase loop is writing. Okay, main driver loop, see virtual task run phase UVM phase. What is your class handle? Okay, class name example transaction, for that handle is transaction. Okay, so then initializing the signals, reset signal, I'm initializing that. So wait for reset to complete. Okay, after that waiting, then main driver loop we are writing. Forever begin handshake method, sequence item port dot get next item transaction, and then displaying that it will show the number of transactions, how many are converted to string, and then driver transactions. Drive transaction is the another task we are calling somewhere else. Okay, then sequence item port dot item done. In this way, the driver class is ended. Then the task is ended. This driver transaction we are writing for virtual transaction. See, virtual task. So task, virtual task, reset signals. Okay. So how we are taking the reset signals? It will be considered that. Okay. So reset signals means whatever address we are considering. Okay, data, write enable, read enable, byte enable, all are connected to 0. Okay, all are connected to 0. And then reset, these are the reset signals. See, virtual task reset signal, we are writing some reset signal right here. Okay, so this is the reset signal, that is in so virtual task we are writing some reset signals. Okay, tick info get type name, resetting the DUT signals, and then this is the description and verbosity level, all are initialized to 0 during reset. During reset operation, it will do that all are initialized to 0. And then wait for reset complete, right? So another task we are writing. Virtual task wait for reset. What it will do in that? Again, get type name, wait for reset, medium none. Then reset, wait if VF dot reset equal to 0. So that means reset is done. If we are writing VF wait VF dot reset equal to 0 means VF dot reset equal to 1 means we are setting the reset operation. After that, we need to release the reset operation. Then reset operation is completed. Then wait vf dot reset equal to, through virtual interface only we are calling the reset signal. Okay, it is equal to 0. Then reset is released. We need to initialize the transactions. Okay. Then task driver transactions we are ready. After releasing the reset, we go for the driver transaction task. Okay, virtual task drive transactions. This is a parameterized. Example transaction is my sequence item class, and then transaction is the handle for that. Okay, if transaction dot is right, it is doing write operation. Then drive write transaction. Else is read. Then read drive read transaction. Again, we are writing some task to drive transaction and read transaction. Okay, drive write. So then I am doing that drive a write transaction. Virtual task, drive write, example transaction, info message, and then at the rate posage vf dot clock. Through clock only we are driving all the signals. Okay, vf dot clock, vf dot address equal to transaction dot address, because we are taking the address, that is the handle transaction. Through transaction class we are assigning the address to virtual interface. Okay, through virtual interface driver will driving the signals to DUT. Okay, so this is the transaction address and then VAF address, and again data we are having transaction data that is assigned to VAF dot data, and then byte enable is there. Transaction dot byte enable is assigned to VAF dot byte enable. Okay, and write enable is there. So if you are doing write operation, write enable is 1 and read enable is 0. So if ready equal to 1, wait for ready means the signal handshaking is happening properly, then data is transferred. Okay, writing operation is completed. After that, write enable should be equal to 0. Okay, at the rate vf dot clock, I am disabling the write operation. After disabling that, you go for some placeholders like response and timestamp we have, right? So then transaction dot pay response okay equal to 1 and timestamp how much time it will take to complete the write transaction. Again, task drive read transaction, virtual task drive read. Okay, example transaction and then transaction. Okay, again, so displaying the messages. Okay, address, transaction address, and then medium. So while reading we need to drive the address only. Through address it is getting the data. Okay, so again, at the rate postage vf dot clock, vf dot address equal to transaction dot address, byte enable, write enable is 0. Okay, that means read enable is 1. Okay, so we are taking the read enable. Okay, we are taking the read enable here. After that, wait for ready equal to 1, and then data read data equal to vf dot data. After that, some read enable equal to 0 if you are completing the read transaction, and then placeholders how much time it will take to complete the read transaction, and then timestamp. Understood? Driver